Live from the University of Texas at Austin, the Liberal Arts Development Studios present Essentials of AI for Life and Society. And now, here are your professors, Joydeep Biswas, Don Fissell, and Peter Stone.
Hi, everyone. Actually, just one of me here today. I'm Peter Stone. And welcome to week 3 of Essentials of AI for Life and Society. Your TA, Zifan, has been looking through the reflections that you all submitted on Monday, and those will be, some reactions will be posted on the edX discussion board. We encourage you to look there and to use that discussion board if you'd like. The instructors are all monitoring that. If there's things about the class you'd like to discuss, we encourage you to do that. Also, as always, there'll be a Q&A session at the end of today that I'll be moderating. I encourage you to enter your questions as you think of them during the class, because that'll give me time to start collating them. So last week, Professor Biswas talked about AI planning, one of the earliest paradigms of artificial intelligence. He gave the example of moving a piano. And the assumption, the main assumption in planning has typically been that the world, everything you need to know about the world to do that planning is known. That you know the state of the world when you start, you know exactly what's going to happen when you take an action. And that was really a very popular paradigm of artificial intelligence in the early years. But people noticed fairly quickly that in the real world, you're not always certain, that there's a good deal of uncertainty. You might plan to take 15 minutes to get to the airport, but because of traffic conditions, it actually takes 20 minutes. And so today, you have the good fortune of hearing from one of our newest AI faculty on campus, Roberto Martín-Martín, who's going to tell you about the next AI paradigm, reasoning under uncertainty.
Thank you, Peter, and thank you, everyone, for attending the new class of Essentials for AI, of AI for Life and Society. I'm Roberto Martín-Martín, and I'm going to be talking about probabilistic modeling. But before we talk about that, let me refresh you on the definition that you were given about artificial intelligence. Artificial intelligence is a science and a set of computational technologies that are inspired by, but typically operate quite differently from the ways people use their nervous systems and bodies to sense, learn, reason, and take action. And you were also told that despite the media, AI is more than just deep learning, so we are going to be talking today about one of these things that are more than just deep learning, which is probabilistic modeling. And in fact, probabilistic modeling is boosting deep learning and many other methods in AI. To give you a definition of probabilistic modeling, is a statistical approach that uses the effect of random occurrences or actions to forecast the possibility of future results. But if you get something from this slide, I want you to focus on this part of the definition of AI. AI operates quite differently from the way people operate. And that is a good thing when it comes to probabilistic modeling, because humans are actually really bad at doing probabilistic inference. And probabilistic modeling will give us the tools to do proper evaluations of probabilities. Why are humans so bad at probabilistic modeling? There are several reasons. For example, we're really bad because we round probabilities very coarsely. Among all the probabilities that could happen between 0 and 100, we tend to simplify into 3 cases. It won't happen, 0% probability. It might happen, 50% probability, or it will happen, 100% probability. This is a very coarse approximation of what actually the probability of event could be. And even though we can deal with that in our daily lives, AI needs to be more accurate predictions of the probability of events. Another reason why humans are rather bad at probabilistic inference is because we are not so good at dealing with large numbers. For example, 1 every 10,000 clovers have 4 leaves. That is a fact from biology. So if we imagine that just a small fraction of people in the world, 0.0001% of the people in the world see a clover every day, from the 8 billion people that are there, 800,000 people would see a clover every day. That means 80 people would find a 4-leaf clover every day, which doesn't sound so lucky as we think is usually to find a 4-leaf clover. So this is because we're not that good at doing calculations with very large numbers. Today in the recommended readings, you saw about these reasons why humans are bad, despite having some intuition about probability. And one of the other reasons that you saw about why humans are bad is because we pay attention too much to certain events and we ignore other events. And that leads to very bad probabilistic reasoning. That was highlighted in an experiment where people were counting basketball passes. So let's have an Instapoll question to know what did they miss, the people participating in the experiment, while they were counting the basketball passes. Let's go to the question. All right, we're back. I hope these initial words gave you some motivation why probabilistic modeling is important. Let me give you some other reasons. The first one we have been discussing is because humans are really bad at computing probabilities in our heads, and probabilistic modeling will give us the tools to do that in a rigorous way. And AI algorithms need to do this inference in a more rigorous way. But why do we need to reason about probabilities in the first place? Well, as Peter was mentioning, the world is not deterministic, as we say. That means that the same actions can lead to different outcomes, or some effects cannot be predicted. Like, for example, where you toss a coin, you don't know what is going to happen. Also, some data is noisy. If you have a car and you are driving, and the car says you are driving 60 miles per hour, it can be plus minus 5 miles per hour of uncertainty. And are the techniques that we have seen so far in this course not enough? As we were discussing, the techniques that you saw in the last day with Professor Biswa's class, they were not assuming any probabilistic outcome. Classic logic assumes that some clauses like if A, then always B. But what happens if sometimes B and sometimes C? There is no way to reason about these probabilistic outcomes with classic logic. Probabilistic modeling will give us the tools to do this in a proper way. So in a nutshell, what probabilistic modeling is going to give us is the tools to correctly reason based on the chances of different events to happen. And this is critical to make informed decisions in AI systems. Let's see that with a very simple example where a simple probabilistic modeling will help us understand the right probabilities. So let's imagine that we have John that has 2 children, and we know that one of them is a girl. It could be the youngest or the oldest. So what do you think would be the probability of the other children to be a boy? Our intuition says it will be 50%, 0.5. But that is actually wrong. And we can see that with a very simplistic probabilistic modeling. Let's enumerate the possible cases. It could be that the oldest children is a boy and the youngest is a boy. That is the case BB. The oldest is a boy, the youngest is a girl, BG, GB, girl and boy, GG, girl and girl. So these are all possible cases for a person that has 2 children. We know that one of them is a girl, one of them is G. So what cases that are equally probable are still valid? So if we take the cases that are still valid, it can be the oldest is a boy, the youngest is a girl, BG, GB, or GG. So if we look at this model, can we answer what is the probability that the other children is a boy? We see that in 2 of the 3 cases, it will be a boy. That means the right value is 2/3. So this very simplistic probabilistic modeling already helps us to battle our initial intuition that was wrong. All right, so what is what we are going to be discussing today? I hope I motivated enough why probabilistic modeling is important, and why is it an intrinsic part of AI. I will give you a couple of tools about the basics of probability, just to give you the language that will allow also in the next classes to understand some of the concepts. Then we will talk about an important concept in probabilistic modeling, Bayes' rule, and a tool that we use in AI that is called probabilistic graphical models. And at the end, I will talk about how probabilities are used in robotics, which is my field of study. Let's get started. So what is a random variable? We say that capital X is a random variable if it can take different values with different probabilities and can be observed with an experiment. This random variable, X, can be continuous or discrete. For example, the outcome of a dice is a discrete random variable because it can take only 6 possible values, while the height of adult population of a country can be also considered a random variable, but is continuous because any value within an interval is a valid value for that random variable. We then talk about the sample space as the space of all possible values that a random variable can take. In our example of the outcome of a dice, the sample space is a set with 6 values, 1, 2, 3, 4, 5, 6. And in our case of the height of adult population is an interval between more or less 1 feet and 9 feet. Any value there is a valid value in the sample space. We then say that P of capital X equal small x, or the probability of an event, or the probability of x taking the value small x, is what we're interested here, is basically the probability of the random variable. So we know that the probabilities are going to be for any event in the sample space smaller than 1, or if you talk about percentages, smaller than 100%. And we also know that the sum of the probabilities of all the possible events in a sample space have to sum to 1 or to 100% if you are talking about percentage. Okay, so what is a probability distribution? A probability distribution is basically the function P of capital X equal X, or what is the probability of the random variable capital X to take the specific value small x. When we plot it with the x-axis, the horizontal axis, having the values of the sample space, and the y-axis having the probability of each of these values of the sample space. For example, the case that you see here is a regular dice where we have 1, 2, 3, 4, 5, 6, and the probability of them is 1/6. We can have an unfair dice, a trick dice, where the probability of 1 is 0.5, and the probability of the other numbers is 0.1, and the probability distribution would look like you see in this other plot. For a continuous random variable, like the height of the population, we can plot for men and women, like we do here. It would be a continuous line because any value in the interval would be a valid value of the sample space. And then on the y-axis, in the vertical axis, we have the probability of each of these values. All right, last round of definitions. What is the mean of a random variable? Mean is also called expected value, and is a value that depends on the numeric value of each sample and the probability of each sample in the sample space. It gives us the value that is the most likely to happen if we repeat the experiment many, many times. And formally, we define it as the expectation of capital X is the sum of the values in the sample space times the probability of these values. Okay, so this sounds very weird, but if we go to our example of the dice, we will see that it's not that difficult. So we just take the different values that the dice can take, multiply by their probability, and we sum them all. So for a normal dice, the mean value of the dice is 3.5. So if we have an unfair dice, the one where the 1 comes out more often, 50% of the time, the mean of this random variable will be skewed towards a smaller value because the 1 is going to be appearing more often. Okay, so with these very simple definitions of probabilistic modeling, we are already ready to take some more informed decisions based on correct probabilistic reasoning. For example, imagine that you are a casino player and you're playing a game where you get as many dollars as you roll with the dice, $1 if you get a 1, etc. So what would be the fair amount that you would pay to play that game? And the fair amount would be the amount that you would be paying so that when you play many times, you are not losing money nor winning money. Okay, let's go into this question. are back. I hope everyone answered $3.5. Why? Because as we computed, that is the mean of this probability distribution. That means if you pay less, you would be winning money. That would be great, but not fair for the casino. If you pay more, you would be losing money. And that will happen when you play many, many times. So why am I saying that you have to play many, many times? That is known as the law of large numbers. That means that the average outcome of an experiment, it tends to the expected value only when we repeat the experiment many times. The mathematical formalism of the law of large numbers, you see that at the bottom, but the important idea, you see it summarized on the right, where there is an experiment where someone is rolling the dice, and you see the number of experiments and the average value of the outcome of the dice, and you see that on the left, when there are few rolls of the dice, the value is not so close to the expected value that we computed, 3.5, but as we do the experiment many, many times, and we get close to 1,000 experiments, the average value that we get is very close to the expected value. All right, let's see another concept that is very important in probabilistic modeling and in AI, dependent and independent variables. Let's assume that we have two random variables. One is x and the other is y. For example, x can be the outcome of a coin toss and y can be the outcome of a dice roll, or x can be the probability of an individual to develop lung cancer and y the probability of that individual to be a smoker. Then we say that P of x, y is the joint probability. What is the probability of these both random variables to take a specific value? We then also say that P of x bar y is the conditional probability, the probability of the random variable x conditioned on knowing something about the random variable y. For example, what is the probability distribution of coin tosses when we have roll a dice and get a 6? Or what is the probability of an individual to develop lung cancer when we know that this individual is a smoker? Based on these definitions, we can then say if x and y are independent variables because the distribution of x is not influenced at all by the value taken by y, and vice versa. In our case, rolling a dice is completely independent from tossing a coin. So if we have the combined probability, is going to be just the multiplication of the individual probabilities, and the conditional probability, knowing that we have rolled a 6, it doesn't affect anything about the coin toss, so it's going to be the original probability again. On the contrary, we say that x and y are dependent variables if knowing the value of one affects the probability distribution over the other. In that case, the conditional probability of one knowing the other is not going to be equal to the original probability. For example, the probability of an individual to develop lung cancer if we know is a smoker is not equal to the general probability of someone to develop lung cancer. So how do we measure if two variables are actually independent or not? We use and we estimate a value that is called correlation. I'm not going to show the mathematical equation here, but you just need to know that it's just working with the different probabilities and the values of the different events, and that if the correlation equals to 0, the variables are independent. If the correlation is not equal to 0, the variables are dependent. The important thing here is correlation can be computed through probabilistic modeling, but correlation is not the same as causation. Causation means that an event is causing the other. If I switch on the switch of a room, the light will go on because it's caused by my action. But in probabilities, if you have correlated variables, that doesn't mean that one is causing the other. And this is important, especially in AI, because sometimes we measure correlation and we think there is a causation, and that is a door for biases and prejudices. So this is an important concept. And I want to give you an example. Let's imagine that we have two random variables, ice cream sales and sunburns. We measure the correlation between them, and we see that they are very correlated. They happen often very at the same time. Does it mean that we get a sunburn because we bought ice cream? No. Does it mean that we buy ice cream because we got a sunburn? Probably also not. So what is going on here? What is going on is in our probabilistic model, there is a third factor that we are not considering. that is actually the cause of these two other random variables. So that third factor is the weather. If the weather is hot, the ice cream sales will go up and the sunburns will go up. But in our model, we don't know about that. So the only thing we can measure is the correlation between sunburns and ice cream. And we should not mix it with causation. A very important concept in probabilistic modeling is called the Bayes rule. The Bayes rule is a method to calculate the conditional probability of one event based on the conditional probability of another. And why would we want to do that? Because it may be easier to calculate one than the other, or because we want to obtain the probability of an event given some evidence, some outcome of an experiment. The form of the Bayes rule is what you see here. And these are all the elements that we have been seeing today. The probability of the random variable x condition on y is the probability of the random variable y condition on x times the probability of x divided by the probability of y. All these elements in the equation have special names. The probability of x given y is called the posterior probability because it's the probability distribution once that we know something about y, about the variable y that we have observed. Px is called the prior probability, which is what do we think about the distribution of the variable x before we know anything about y. P of y given x is called the likelihood. What is the probability of observing y knowing something about x? And P of y is called the evidence, the probability of observing that in the first place. Then we can write the equation in that more English-like way. Posterior equals to likelihood times prior divided by evidence. So this sounds very complicated. I want to give you an example that actually is likely is not so trendy anymore, but it was very trendy a few years ago. So let's imagine we have two random variables. One is C, which is to be positive on COVID, and the other is T, which is to have a test result that is positive. So let's imagine that the problem is a randomly selected patient takes a test, and the test comes back positive. So what is the probability that this patient has actually COVID? So we are given what is called the test sensitivity, the probability of the test to be positive, conditioned on the person to be really sick, and that is 85%. Is that the probability that the person that we pick randomly has COVID? No, it is not. What we actually want to figure out is what is the probability of the person to be really sick, C equals true, given that the test is positive. And that is the conditional probability we want to compute based on the other conditional probability. So we will need a couple of additional probabilities to compute that. What is the general probability of a person to have COVID, which is very low, 0.02, and what is the probability of a test to be positive in general, which is 5%. Using that, we can just apply the Bayes rule, and then we obtain a result that the probability of the randomly selected person to be actually sick of COVID would be 0.34%, which is a huge difference compared to the 85% probability that is the test sensitivity. Why is that? Because the test sensitivity doesn't tell us anything about how probable it is in the first place that someone is sick of COVID or not. So this is a very important difference, and thanks to probabilistic modeling, we can understand the right probability. So we have been discussing very simple conditional probabilities of two variables, but in AI, we use actually very complex networks of dependency. And for that, we represent them with probabilistic graphical models. In these models, each node is a random variable, and they are connected with an arrow if there is correlation between them. So in this way, we can compute complex conditional probabilities, like what is the probability of having the flu if we know the season and that the person has congestion. There are very complex probabilistic graphical models, like the one that you see here, that is used to predict the liability cost for someone based on their age, the mileage, the vehicle year, etc. So probabilistic reasoning and probabilistic modeling is a critical component of many AI techniques, from Bayesian linear regression, active learning, reinforcement learning, planning, etc. And many of those are techniques that you are going to be looking at in the next classes. But I want to give you an example from my field, which is robotics. And In that field, probabilistic reasoning is critical. Robots should make decisions based on the uncertainty of the information they have. That's why probabilistic modeling is an intrinsic part in robotics for perception, localization, robust reasoning, control, etc. A very successful case is the case of probabilistic localization. And I'm going to give you an example here. So imagine that we have a robot in a corridor, and the robot doesn't know where it is. So we represent the location along the corridor with the variable x. The robot knows about the form of the corridor, the length, the doors, so it has a map of the corridor, but it doesn't know where it is in this map. That is what we call the localization problem. The belief of x is where the robot believes it is, and is what is indicated in that graph underneath the picture. So we know that the robot is in front of the first door, but the robot doesn't know that. The robot has a sensor that tells when it is in front of a door. And initially, because the robot doesn't know where it is, all points in the corridor are equally probable. The belief is all spread out. So let's imagine that in a first step, the robot receives a sensor reading, and the sensor reading says, hey, you are in front of a door. The likelihood of that event is the probability of reading I'm in front of a door conditioned on the different locations along the corridor, which is the red graph that you see in the plot. And based on that likelihood, we can update the belief of the robot to be the exact same as the likelihood. So the robot thinks I'm in front of one of these doors. So that's why there are spikes in the probability in front of the doors. So now let's imagine that the robot moves a little bit to the right. So the belief moves with the robot. So if it thought it was in front of the door at the right, it will think now that it's 2 meters past that door. So the robot then receives a new signal. Hey, you're in front of a door again. The likelihood is again the same. So the red graph is exactly the same. There are spikes. You can be in front of any of these doors. But the belief of the robot gets updated correctly. So by knowing the previous measurement and the current measurement, it can infer the posterior in the right way, knowing that there is a spike of probability. The most probable location is in front of the second door. Now that the robot knows where it is, it can move forward and propagate the right belief, knowing where it is along the corridor. And that means it has localized itself correctly. So this sounds very toys, but it's actually how robots work in the real world. So here we see a picture of a robot in one of the Austin restaurants that are using robots for helping. And instead of having a sensor that tells you are in front of a door or not, it has what we call a LiDAR, which is a sensor that gives information about the distance at different points around the robot. So what this robot has is a map of the environment that you see here in a top-down view. And initially, it doesn't know where it is, like the previous one. So we represent that with different hypotheses that are these small red dots. Each red dot is a hypothesis. So initially, it's all spread out. It doesn't know where it is. The green dot is where there is the maximum likelihood. So that means the robot thinks among all these hypotheses, I think I'm here. And the blue arrows is the LiDAR sensor that is giving some information about the depth around the robot. And it's sometimes noisy, so it goes through the wall. So if we look how probabilistic localization works in the real world, we see here how the robot is changing its belief and is collecting more and more information, more measurements from the LiDAR, more of these blue lines, reducing the uncertainty about its location. So many of these hypotheses, the red dots, are disappearing until the robot is just converging to one possible location of where it is in the environment. And this is because as it moves, it reduces the uncertainty. So finally, it converges to a single location. That is, all these points are in one hypothesis. That is where the robot is actually located. So let's go to our last insta-poll question to know what are these dots representing. All right. So what is the summary of what we saw today? I gave you at the beginning some reasons why we want to have probabilistic modeling in the first place. Then we went over the basics of probability: random variables, distributions, dependent and independent variables, correlation versus causation. We saw the base rule and some examples, and what are probabilistic graphical models. And finally, I gave you a couple of hints of how probabilistic modeling is used as an intrinsic component of robotics today. That concludes my presentation.
All right, thank you very much, Roberto, for that fascinating presentation. And it included both an introduction of probabilistic, probabilities in general, which may have been familiar to some people, but I think was probably new to others, and then exactly how it's applied to AI. We have some questions starting, and I encourage the rest of you to enter into the chat. The first one was, how do we choose what random variables to include in these graphical models? At what point would we have too many variables or potentially too few?
Yeah, that's a very good question. And as we were discussing when I was giving you an example of correlation versus causation, not including the right variables could be very problematic. So part of the art of using probabilistic modeling is to be able to model correctly the world. What are all the variables that have to be represented and that are important to understand the correlations between all the existing variables and infer the right probabilities, basically.
And in some sense, every model is an approximation, and so you can never model everything, right? You can't model all the positions of all the air molecules, and so that's part of the art of. And we sometimes say that in artificial intelligence, there's sort of the science of it, and there's also the art of it. Like what parts are you going to put into the model? So. Another question was, in the case of the doors, it was a fairly simple example, but what kind of information is the robot gaining as it goes through a restaurant to be able to localize itself?
Yes, that's a very good question. So the information that it gets, if you remember the animation, it's getting different LiDAR measurements. So by looking at how the pattern of LiDAR measurements fits into the map that the robot has, it can infer which ones of the hypotheses are more likely or not. So if I see with my LiDAR sensor that was this blue rays, indicated with these blue rays coming out of the robot, that there is something 2 meters in front of me, but one of my hypotheses says there should be something at 1 meter, that means this hypothesis is probably not the right one. So it decreases the probability of that hypothesis. So by collecting more and more of these informations, prunes out the hypothesis, keeps the ones that are the most likely until it converges.
And there's a follow-up question to that, which is actually very astute. And that question is, how does this kind of method, localizing in the restaurant, account for the movement of people? Which the people might block these, the known locations of things.
Yes, that is a very, very difficult question. Not difficult question, but difficult problem in localization. And that is not part of what the robot is taking into account. So if there is a few people, that can be considered noise of the sensor. If you remember, we assume that the sensor is noisy. Some of the rays can go through the wall, even though there is a wall there. So most of the signal of the sensor is not noise, but there could be some noise. And people can be considered noise within the map because are things that are not in our model, not in the model of the robot. If there is a lot of people, suddenly there's a circle around the robot, which is something that happens very often because people are very excited about robots, then the robot is not going to be able to localize because it's not going to see any representative pattern of the map. It's just going to be a circle around them. So yes, people are noise for the robot because they are not mapped. There are some techniques to try to compensate for that with dynamic changes of the map, but in general, for classical localization, is a big problem.
There's a bunch of interesting follow-up questions also about the creation of the map in the first place. So One person asked, did someone have to code the environment for the robot to recognize its location, or is it learning doing probabilistic modeling? How would a robot map itself without initial localization? Does the robot have to map, build the map as it goes along? What if there isn't a pre-existing map?
That is a very good question, and it's a very robotics technique. One of the most robotics techniques we have. Robotics is usually taken from others, but there is a technique called SLAM, simultaneous localization and mapping, that is exactly doing that. So the robot initializes without any map, so it has to build a map at the same time that it's localizing itself within that map. So that is a way we can have a robot that goes into a new environment and is able to map this new environment, and once that it has mapped it once, it can just localize. But if it needs to create the map at the same time that it localizes, we use a technique called SLAM, simultaneous localization and mapping.
So
I think there's a question here.
Oh, yeah, question in the audience.
I was wondering if you could give an example of probabilistic modeling with autonomous vehicles.
Yes, autonomous vehicles, depending if they are using a map, they will also be localizing themselves within the map. Some other ways in which probabilistic reasoning can be used is to, for example, recognize pedestrians or different objects. So when a computer vision algorithm that is helping an autonomous robot is making inference, it usually takes into account the uncertainty about what is perceived. Is this a person? Is it not? It's usually not a binary signal. It's rather a probabilistic value. So the agent can make decisions, the car can make decisions based on that. Probably not in terms of if an obstacle is a person or not, but how probable it is that the thing that I'm seeing here is a rock in the middle of the road or not. How accurate I am in perceiving it, how probable is that I find a rock in the middle of the road. So these are ways in which autonomous cars would use probabilistic modeling.
And in fact, they do. Just last night, I drove by five cruise cars in a row, so they're all over Austin right now. There's a follow-up question on that. In the case of self-driving cars, how does the robot car manage road closures or other significant differences that are not in the map?
That is a big problem, yes. Our map is supposed to be our ground truth model. If there is something that is different than it is in the map, then we cannot just work with localization. We need to have perception. Perception is our connection to the real world, to the current state of the real world. So in autonomous cars, for example, there is a combination between localization with a known map and real-time perception. My map says there is a road here, but my real-time perception says there is a construction work, therefore I'm going to stop. So it's a combination of different, basically perceptual algorithms here.
But as a follow-up to that, it's also the case that the robot could take into account maybe reports on where there is construction going on, and then if it perceives a road closure, or thinks it perceives a road closure, it might be able to say, oh, I don't actually think it's likely that there's a road closure here because it didn't appear on the city report, or it's more likely that there is one here. So the probability that a particular road would be closed can also feed into the reasoning.
Yep, that's right.
An interesting question also is could a robot get lost in a round room with a symmetrical map pattern within it?
Yes, that is correct. If the robot is using just geometry to localize itself, and there is no significant pattern that tells the robot where it is, it's not going to be able to localize. But that would be the same for a human. Imagine you are in a round room without any visual pattern, without anything that you can see that is all a white wall. If I turn you around, you open your eyes, can you say in which direction you are looking? It's impossible. There is nothing that is distinctive enough to tell where you are. So that is the same for the robot, but the robot doesn't see in this case, with RGB cameras or with color cameras, but it's just looking geometry. It's looking just the distance to the different points in the environment.
So there's a couple more questions along these lines that I want to get to, but I want to make sure we have time for a question of a completely different nature, which is how is robotics as a field supposed to help us with understanding human intelligence, perception, et cetera, if it functions differently from us?
Well, that is a very good question. It's a difficult one. So I was collaborating at some point with some biologists, and they were actually behavioral zoologists, sorry, and they had some models about how cockatoos, how the birds explore the world. So they came to us to try these models on a robot. So there's some levels where robots and humans or robots and animals are gonna act very differently. But there is always some level of abstraction where they could be compared. So for example, the behavior. What a robot does is to go into the world and act. So you can measure what the robot is doing, and yes, the internals of how it's working may be different, but there may be some connection. So we can test some cognitive systems, some ideas about how humans do things on robots, although there will be always some differences in the morphology, in the way the robots interact, in the way the robots reason about probabilities, etc.
And I would follow up too, that, and I'll come to you in a second. It's not necessarily that AI is just about understanding human intelligence.
Yeah.
The artificial intelligence, as we covered in the first lecture, is about understanding intelligence, the nature of intelligence.
Yes.
And so the way people do it isn't necessarily the best way. As Roberto gave good examples before, people are not great at reasoning about probabilities. Mm-hmm. So it may be that we can learn about the sort of possible ways of doing intelligence by building robots that are beyond what people can do, we find interesting observations where people are better than robots at some things, and robots are better than people at some things. But both of those are about intelligence in general.
Yeah, and I would say intelligence is just generated intelligent behavior. It's very behavioralist, but if what the robot can generate, we consider it as an intelligent behavior, that is to me a demonstration of intelligence, no matter how it is created, if it's exactly how we do it or it's slightly different.
Yeah, please, in the audience.
So in regards to augmented reality, is localization and like more specifically just like SLAM in general utilized to be able to like map out those environments and be able to like map on like images onto your environment around you?
Yes, so for augmented reality, the important thing is to know where the camera is looking. So if you create some virtual element in the environment and you move the camera, the virtual element should remain in the same location in the real world. So what is used in there can be seen as localization in the 3D world instead of kind of like navigating like the robot that we saw in the example, but it can be solved as a form of 3D localization. Basically, where is my camera right now looking at in this environment? So yes, we can use similar techniques.
Good. So another question that someone put in the chat was, how do robots avoid being trapped like old robot vacuums?
Well, the old robot vacuums, they don't even do localization as we have seen here. So they just use random patterns. So they go in a straight line until they bump into something, they turn around some random angle, and then they go in a straight line. So that is prone to get stuck into some corners. Some more newer versions of the vacuum cleaners, as far as I know, they create maps, and they can even semantically annotate these maps. This area is an area where I don't want to go for whatever reason. I can get stuck, or the person told me to not clean that area because it's not something I have to clean. That is done with a map, and then the robot can localize within this map using LiDARs or using cameras. But yeah, the old ones, they don't even have a map. They don't even care where they are in the world. They are just randomly going in many directions until they have covered the entire floor, and sometimes they get stuck.
So it's, today's talk was about probabilistic reasoning. Not all robots are using probabilistic reasoning.
Exactly.
Some may, some not. We will have a class devoted to intelligent robotics later on. So I'll defer. There's a couple other questions here about robots in general that will be good for that time. There's another question about going a little bit deeper into SLAM and how that works. The person who asked the question said there's both uncertainty in the robot's position and it's an environment. So how does the robot reconcile this in real time?
Well, this is a very good question. It's kind of like a dual problem. How do I localize based on this map? How do I map based on my localization? And both of them are noisy. So yeah, it's a combined, let's say, optimization, probabilistic optimization problem, where it's building slowly the map based on the most likely location. But yeah, there are different techniques to do that. Yeah, it all boils down to estimating at the same time the most probable map together with the most probable location within that map. Yeah, the math is a bit more complicated, but it's basically a long, complex, conditional probability of the location based on the probability of the map and vice versa. So yeah.
There are some good videos online about how SLAM works, and one of the classic sort of techniques that happens is what's called loop closure. Yeah. A robot will sort of go around a loop, and it's building a map. It's sort of uncertain, but then it gets back around that loop to a location that it started at, and now rather than being sort of skewed, everything sort of comes into place. It knows that it's rectangular. It's hard to get it from my description, but if you go to some videos about SLAM working online, you can find that. But the mathematics of it is quite complicated. Yeah. In one of the old robotics courses here at UT, a graduate robotics class, that was the main final project, was for students to be able to program up a system to do SLAM. Mm-hmm. So,
but this loop closure is a good example because I have this loop closure sometimes. I go around the city and then I discover, oh, if I go this way, I connect with this other street that I didn't know there's a connection here. So I kind of like redo my map because now I know there's a connection here that I didn't know exists. So yeah, I think we also humans do this type of loop closure when we are building our mental maps of how to navigate a building or how to navigate a city and small streets.
Yeah, and so, I mean, today was all about probabilities, and it doesn't just come up in robotics. It comes up in statistics and economics. It also comes up, as you said, in psychology and how people are. And so there's another question here about, that says, I understand that we as people are not good at articulating probabilities, but would you say that our daily micro decision making implies that we have an intrinsic understanding of probabilities?
Yes, and that was one of the extended readings for today. Some scientists went into populations that didn't have any formal education about probabilities, and they figured out that they can do good inference about probabilities, some coarse probability inference. So yes, I think we can do some probabilistic inference. We are not completely bad in doing that as humans, but as I mentioned at the beginning, we're very coarse on how we do probabilistic reasoning. With formal methods like probabilistic modeling and the things that we do in robotics, you can get very accurate probability. So you can really differentiate between an event that has a probability of 15% and another that has a probability of 10, and really take the most wise decision for the robot in that case. While for humans, we may round everything to the same kind of like type of probability, and we will go with that.
Maybe I'll take one more question before we wrap up. Also about robots, and going back to self-driving cars, someone asked, in the last 2 weeks, people in a hurry have run right in front of the car I was in. Can sensors respond quickly enough? Can the sensors on self-driving cars respond that quickly?
Yes. So the same sensors that are used for localization, they are used for real-time perception. The LiDARs that I mentioned, these 3D sensors, they are used for both localizing in a map and at the same time for detecting what is in front of the car or on the side or in the back. These are these towers that you see all autonomous cars tend to have. Inside of that, there is kind of like a rotating thing very quickly that is, excuse me, sensing what is the distance to the different obstacles. So it's exactly that sensor that is used for localization that can sense if you go in front of the car. So it will stop because it will see you, or at least it will try to stop unless you really jump in front of the car too quickly.
Okay, good. So thank you very much, Roberto, for covering this reasoning under uncertainty. So far you've seen planning, where we are certain about things. Today, reasoning under uncertainty. And the next 2 weeks, we're going to be introducing you to machine learning, which has come to become one of the most dominant paradigms. And there's a slide on this if people want to move to it. Yes, thank you. And so there'll be 2 weeks, first from Adam Clivens and then Ray Mooney, first covering the fundamentals of machine learning and then the different machine learning paradigms. But this really is what many people think of now when they think of artificial intelligence is machine learning these days, and that's what you'll be learning about in the next 2 weeks.